Hello everyone. Today we are referring to evaluation of transfer coefficients using engineering correlations. Till now we have learned about flow past a flat plate, flow past a single sphere, flow normal to a single cylinder. In today's video we are going to learn about flow in circular pipes. So let's get into it. Introduction. Circular pipe flows involve the movement of fluids through pipes with a circular cross sections. It is characterized by mainly various flow regimes, pressure gradients, and efficiency factors. Type of flows in a circular pipe involves a laminar flow, turbulent flow, and transition flow. Laminar flow. It occurs at a low velocity of Reynolds number below 2100. Its characteristics mainly involve fluid layers slide smoothly, parabolic velocity profile, maximum velocity at center, and zero velocity at wall, that is no slip boundary condition. Turbulent flow generally occurs at higher velocity. Its Reynolds number is above 4000. Its characteristics are chaotic motion, formation of eddies, increased friction, and higher energy losses. In between laminar flow and turbulent flow, there comes transition flow. It has a Reynolds number between 2100 and 4000. It has an unstable behavior and flow characteristics vary between them. The key equations and principles are Bernoulli's equation, Poiseuille's equation, and Reynolds number. Bernoulli's equation states that for incompressible and steady flow, the sum of pressure energy, kinetic energy, and potential energy per unit volume is constant along a streamline. That is P plus half rho V square plus rho GH is constant. P is the pressure, half rho V square is kinetic energy, rho GH is the potential energy of the fluid. Similarly, Poiseuille's law states that the laminar flow rate of an incompressible Newtonian fluid through a long cylindrical pipe of constant cross section is given by the formula Q equals to rho pi delta P r to the power 4 by 8 neta L. Neta L. Here delta P is the pressure difference, neta is dynamic viscosity of the fluid, L is the length of the pipe, and R is the radius of the pipe. Reynolds number. Reynolds number is given by rho VL by mu. Here V is the characteristic velocity, L is the characteristic length, mu is the dynamic viscosity, and rho is the fluid density. Factors affecting flow. Friction factor, pipe diameter, fluid density, viscosity, and average velocity determines the flow, whether it is laminar, turbulent, or in between transition flow. Pressure gradient. In fully developed flow, pressure gradient is constant. It determines the flow rate and also determines the energy losses. Engineering correlations and momentum flux. We use macroscopic energy balance to get the rate of work done to pump a fluid is given by rate of work equals to mass flow rate into work done. That would be equal to mass flow rate into integration of volume into dP. This would give the equation work rate equals to mass flow rate into specific volume into delta P. Here specific volume is given by 1 by rho, and this is a constant value. For incompressible fluid simplification, we write work rate equals to Q into delta P. Here Q is the volumetric flow rate. Drag force relation. Drag force, or we call it FD, into average velocity would give us volumetric flow rate into pressure drop. Now, Drag force can be written as pi dl into half rho v square into f. So this would give us the equation pi dl into half rho v square f into v equals to q by q into delta p. Simplifying the equation further, we get del p equals to 32 rho L f q to the power 5 q to the power 2 by pi square d5. Definition of friction factor. Friction factor is a dimensionless quantity that represents the resistance to the flow of a fluid in a conduit due to the effect of viscosity. It plays an important role in fluid mechanics calculation, particularly in determining the pressure drop or head loss in a fluid system. There are two types of friction factor: the Darcy friction factor and Fanning friction factor. Darcy friction factor is a commonly used in engineering application and is represented by the symbol FD, whereas the Fanning friction factor, represented by FF or simply F, is 1/4 the value of Darcy friction factor, that is FD equals to 4F. Laminar flow correlation. For laminar flow, Re equals to d into V rho by mu should be less than 2100. This is the range of Reynolds number for laminar flow. So the solution of the equation changes the and gives us the value F equals to 16 by Re and Fd equals to 64 by Re. For turbulent flow correlations, there exists no theoretical solution for turbulent flow. The friction factor is usually determined by Moody chart given in 1944, in which it is expressed as the function of Reynolds number and relative pipe wall roughness, that is upsilon by d. Or we could also use Colebrook equation given in 1938. This is the Colebrook equation. It contains friction factor F, upsilon by d. This is relative pipe wall roughness. Now let us look at the types of the engineering problem. First is to determine pressure drop or pump size. Here pump size is nothing but the rate of work done. Second type of problem is where we determine the volumetric flow rate, that is Q. And third type of problem, determination of pipe diameter. This is for the laminar flow. First, we determine pressure drop. Here given parameters would be pipe diameter, flow rate and fluid properties. Fluid properties contain the density of the fluid and the viscosity of the fluid. We use the equation of delta P as stated. Delta P equals to 32 rho L F V square upon pi square d to the power 5. This equation was derived from the equation of drag force, which was Fd into V gives us Q into delta P. Solving this further, we got the equation of delta P. Now we have the equation of Re as rho V d by mu. Here V could be written as Q by pi d square to the whole power whole divided by 4. Putting this value of V into the Reynolds number formula, we get Re equals to 4 rho Q by pi mu d. Now using the above equation of Reynolds number in laminar flow correlation, that is F equals to 16 by Re, we get F equals to 4 pi mu d by rho Q. Similarly, we get the delta P equation equals to 128 mu LQ by pi d to the power 4, and the rate of work done we get 128 mu LQ square by pi d to the power 4. Second type of problem we have is to calculate volumetric flow rate. Here given are delta P, diameter of the pipe, and the fluid properties. Rearranging the equation of delta P we got earlier, we get Q equals to pi d to the power 4 into delta P by 128 mu L. Similarly, the third type of problem we have is calculation of diameter of the pipe. Here we have given delta P and volumetric flow rate, also the fluid properties of density and viscosity. Using the earlier equation, we substitute and get the value of D in terms of volumetric flow rate and delta P. This is the relation we use. Now for the turbulent flow. First kind of problem is to calculate delta P or W, the rate of work done, where given would be volumetric flow rate and diameter of the pipe. For the given values of Q and D, the Reynolds number can be calculated using equation 3.11, which is Re equals to 4 rho Q by pi mu d. However, when the values of Re and epsilon by d, that is relative pipe wall roughness, is to be determined using the equation 2.4.1, which is the equation Colebrook equation, which has friction factor on both sides of the LHS and RHS and in relation with Reynolds number and roughness, relative roughness. So it requires an iterative procedure since F appears on both sides of the equation. To avoid iterative solutions, efforts have been directed to express the friction factor F as an explicit function of Reynolds number and relative pipe wall roughness, that is epsilon by d. Two scientists, Gregory and Fogarty, in 1985 compared the predictions of 12 explicit relations with Colebrook equation. This is a Colebrook relation and recommended the use of correlation proposed by Chen in 1979. This relation was friction factor in terms of epsilon by d and Reynolds number with a constant A. The constant A can be calculated using the equations which also contains epsilon by d value and Reynolds number value. If we get the friction factor, we can easily calculate the pressure drop, the volumetric flow rate, or the diameter of the pipe. For this question, we have to calculate pressure drop, and the given is volumetric flow rate and diameter of the pipe. So, in order to calculate the pressure drop, the following procedure would be followed. Calculation of Reynolds number using this equation. Reynolds number equals to 4 rho Q upon pi mu d. Let us understand this with an solved example. Example 4.12 of modeling in transport phenomena. What is the required pressure drop per unit length in order to pump water at volumetric flow rate of 0.03 meter cube at 20 degrees Celsius through a commercial steel pipe of epsilon equals to 4.6 into 10 to the power minus 5 meter, 27 centimeter in diameter. Here diameter is given 20 centimeter. Volumetric flow rate is given as 0.03 meter cube. Here we have to calculate pressure drop per unit length. So let's get into it. The fluid properties of density and viscosity are given to us in the question. Firstly, as the first step, we calculate Reynolds number from the given parameters, that is density, volumetric flow rate, viscosity and the pipe diameter. We get Reynolds number to be 191 into 10 to the power 3, which is much greater than 4000. So the flow is a turbulent flow. For turbulent flow, we studied earlier two equations to get the value of friction factor. Using the A equation, using the values of epsilon by D and Reynolds number calculated earlier, we get the value of A, which comes out to be 1.38 into 10 to the power minus 4. Substituting the value of A to get the value of friction factor in this equation, we have epsilon by D and Reynolds number. We get friction factor to be 4.36 into 10 to the power minus 3. Thus, we have the equation of pressure drop across the pipe length as delta P by L. This is pressure drop across unit pipe length equals to 32 rho F Q square pi square by pi square into D to the power 5. Substituting the value of density, friction factor as calculated, volumetric flow rate is given to us, and the pipe diameter is given to us. We get the value of 40 Pascal per meter. This is the pressure drop per unit length of the pipe. Now, second type of question we get is to calculate the volumetric flow rate, and given is delta P and D. In this case, rearrangement of equation 3.1, that is delta P equals to 32 rho LF Q square by pi square D to the power 5. This equation gives us F equals to Y by Q to the whole square. Here Y is defined as pi square D to the power 5 into delta P by 32 rho L whole to the power 1 by 2. Simply substituting equation 3.11, that is Reynolds number equation of Re equals to rho V D by mu equals to 4 rho Q by pi mu D, and 2.414 is the Colebrook equation. We get the value of volumetric flow rate as minus 4y log of epsilon by D upon 3.7 plus mu D by rho y. Calculate the y from the above equations given and substitute this in the equation of Q, and we get the volumetric flow rate. We have a solved problem of example 4.3 of modeling in transport phenomena. Third type of the problem, we have calculation of pipe diameter given delta P and volumetric flow rate. Many scientists have presented their explicit equations to solve the problem of this type. However, these were unnecessarily complex. A simpler equation is obtained using a suggested method by Dawson and Akagin in 1993. This is as follows. The equation 3.1, which was the friction factor equation, given as F equals to 4 pi mu D by rho Q. It is rewritten as F equals to dn to the whole power 5, in which n is pi square into delta P upon 32 rho L Q square whole to the power 1 by 5. For turbulent flow, the value of F changes between 0.00025 and 0.01925. Using an average value of 0.01 for F gives a relation between D and N as follows, which is D equals to 0.4n. Substituting this gives us the value of d in terms of epsilon, q, rho and n. Epsilon, rho and q are given to us in the problem, and n, as we calculated earlier, we get the value of d. So the procedure simply becomes calculation of n using the above equation, which is d equals to 0.4 by n, and substituting this value of n in the equation of d, we get the pipe diameter. A sample problem is given in modeling in transport phenomena. Example 14.14.